Hello, my name is Hunter Free, and I'm with the Regolith Removers. We're a team for Aero Design One, and this includes
Andy Rodriguez.
Kyle Lackey, Christopher Roswell.
and today we're going to be going over wrong side. And today we're going to be going over a couple different topics from our project, starting from the background to current solutions, our design, and future applications of said design, and also how it works. So first things first, the background for this mission is it's being developed for the Artemis lunar missions. These lunar missions are America's return to the moon, where we seek to establish a long-term presence in the form of either research bases, exoplanet habitation, asteroid mining, refueling bases, and other projects like Gateway, all in an attempt to figure out how to push humanity deeper into the solar system. This all sounds well and good, and the progress is pretty much ready to go by 2027. However, there is one major roadblock, and that is plume surface interaction. That's where the Human Lander Challenge comes into play. This is an international call for aid by NASA to all types of graduate and undergraduate teams, asking them to brainstorm different ideas to tackle different aspects of the lunar regolith problem, whether it be from the hull integrity to vision to just mission systems, anything in between. This is incredibly important because with so much brainstorming, it allows for many different ideas to come forth and hopefully tackle this problem before Artemis's launch time. There's a couple different project requirements. For probably the most obvious one is it must be able to survive in the lunar environment. It's a harsh environment and systems need to be robust enough to survive in sub-zero conditions. It also needs to be designed usable for NASA and private contractors to actually integrate onto their aircraft without any extensive retrofits. It needs to have no risk to crew. And it needs to be within a 3 to 5 year timeline from design, building, and integrating it into the launch vehicle to correspond with their current timeline of when Artemis is actually expected to lift off. It also must be cost effective because money doesn't grow on trees, and NASA doesn't want to spend any more of its budget than it already has trying to get us to the moon.
Yeah, so throughout our design process, we had to look at the different types of plume to surface interaction hazards that can happen. We had to tackle vision obscurity, which can make it difficult for the crew to land on this lunar surface since it's not perfectly flat, since there's a lot of craters, and this can make it difficult for them to find a safe place to land. And there's a historical example of this on the Apollo 14 mission, as they landed on the edge of a crater and the lunar lander wasn't perfectly upright. You could also get false readings, which can cause the scientific research to be in jeopardy. You also get clogging, which can harm the mechanical components of the lunar landers, making it difficult for them to perform accordingly. And there's the plethora of different health hazards from the plume to surface interactions and from any exposure to lunar regolith. Since the astronauts can breathe it in, it can cause respiratory issues. It's also an eye irritant. And since there's no weathering on lunar surface, the lunar dust particles are actually very sharp and can damage the skin on contact. Despite all these problems, we wanted to primarily target visual obscurity since we believe that it's a problem that's not being tackled hard enough from the current designs. And we think that with the current designs available to actually solve this problem, there's still gaps in these solutions, so they cannot be understated. So the current technology, we have a few examples here. You have electrodynamic dust shields. This uses an AC current along an array of electrodes to generate a dynamic electric field, which prevents adhesion of lunar regolith and is currently used on the ISS, as you can see from this before and after picture on the top right. You also have electrostatic lunar dust collectors. This uses an array of electrically charged plates to attract any lunar dust, and it's used to prevent dust collection on top of solar panels, as you can see on the bottom right. There's also electron guns, which uses a beam of electrons to localize a charge and to repel lunar dust over time. You also have brushes, which in the early days of Apollo, they were primarily made of nylon, and they were used on the Apollo 14 thermal degradation sample. But there's current blind spots in these technologies. Most of them only affect ferrous materials. They are complicated technology and require specific designs for them to be implemented. Since they have their own caveats to them, the electrodynamic dust shields use up a lot of energy and they have high voltage, so it can cause a risk to the crew. For the dust collectors, they have strong magnetic fields, which can cause disruptions in the instruments on board the lunar landers. The electron guns can also damage any structures nearby. And also, most of these designs do not tackle our main issue that we're trying to look for, which is when the lander is actually landing. They all use a lot of power consumption and they weigh a lot, since some of these are these big arrays of electrodes or plates.
So with all these current technologies and all these current blind spots, when we were initially designing this concept, we wanted to design it with two primary goals. The first one was to have simplicity in mind. This allowed it for both easy building and easy integration within current systems, without causing unnecessary hassle for the engineers at both private corporations like SpaceX and NASA itself. We also wanted to be flexible in application. While initially we did choose the Starship launch vehicle, we wanted to go past that, not only tackling different sections of the vision systems, but also tackling the hull integrity, landing systems, and other stuff, and also allow it to work on other landers and even lunar assets such as extraterrestrial habitation, rovers, solar panels, anything that you can think of. So through our research, the only material that we found that really accomplished this in any stretch of the imagination was piezoelectric plates. And that's what we decided to base our entire design on.
Right, so what PZT really is when you apply an electric field to the PZT, it causes the material to expand and contract. And depending on the frequency of the electric field in question, it will vibrate faster or slower. Right now, that effect is being used in ultrasonic cleaning. As you can see in the video on the bottom right, it uses cavitation bubbles to clean the material. It has not yet been utilized for space travel. The idea and concept itself is relatively new, so its potential hasn't been fully realized. Even our design can be applied to other things. It has more use than even what we've established. So in a research article that used this concept, if you see right here, might be a little hard to see, but the dust all came out when they tested it. The effectiveness was at least 90%, but more likely within the 95 to 99% effectiveness, which is what we would estimate for actual practical use. We have adapted that kind of concept of using the PZT plates for space travel and on the aircraft itself. It will be placed on the corners of the windows, and that vibration should allow for the same effect shown there. Instead of using the cavitation bubbles, as mentioned in the ultrasonic cleaning, it's using conduction, so it's a different system than what's being currently used. Right, so the frequency at which the PZT is actually effective for dust removal is in the 30 to 80 kilohertz range. Now, I couldn't find exact information on the material used in the SpaceX ship because they don't show that to the public. But based on similar materials, I could estimate that it's going to be somewhere in the 100 to 3.2 kilohertz range for the resonant frequency of the window itself. That means there will be no overlap. There shouldn't be any problems. The best effective range, though, is in the like 30s, like low 30 kilohertz range is usually where it's at the most effective. So what it'll do is it'll vibrate that window, and any particles that are already adhered to it will bounce off, and any that would adhere to it will also bounce off. So there should be, as I said before, almost no particles, like 99% no particles, essentially. All right, so the concept design and it does look simple. And really what it is you have the component box with a voltage amplifier and a signal generator in it. There will be wires running from that to the PZT plates. As I said before, they'll be on the corner so as not to block any visual systems. So we'll place it there with the wiring and stuff, and then it will be bolted onto the ship itself. Relatively simple and effective. I think I have one more. Oh, is it?
So to simulate as a proof of concept, to show that this would work, we wanted to try to find a design that would make it work very similarly. Now, due to the monetary cost of PZT plates, at least for small scale research, we had to scale down the model pretty considerably. Instead of using a piezoelectric plate, we used a vibration motor. This vibration motor generated obviously vibrations by having an offset weight on a brush, on this case, a brushed motor. And that allowed it to cause the plate, in this case, plexiglass, to vibrate. As you can see in the video, when it cycles back around, the experiment was we just poured dirt collected from outside onto the plate that's already vibrating. And you can actually see the particles being vibrated off said plate and falling off. This showed a proof of concept showing that vibration is actually pretty effective in terms of cleaning dust, even though it's a much scaled down. We also use plexiglass instead of standard glass, similarly for the same reasons that we couldn't use an actual PZT plate. The model does also scale up as well. We tested it with bigger pieces of Lexon or Plexi or whatever we had on hand, and it actually was able to continuously vibrate those particles off, even though the sizes got bigger.
So the system is supposed to tie into the existing power system. It should seamlessly flow into the existing systems. It's not built to change the ship. It's not built to change any of the systems. It's built to work with them. So it'll tie in the power system. It's relatively minimal power, so shouldn't affect it too much. It's not going to obscure the camera systems or any visual systems it's placed on because they will be placed in the corners, so it's not to block any view. So it should work with the systems already in place as like a secondary option.
So for the structural analysis, we really wanted to focus on the PZT plates because it's the only part of the design that's going to be undergoing any real mechanical loading due to the applied voltage. And this is going to be because of the inverse piezoelectric effect that's going to be driving the plates, causing oscillations, which will induce stress and strain. And it's really important for your applied voltage to not exceed the dielectric strength of the material, which this is going to be the voltage level to where you're going to lose all piezoelectric effects in your material and it's going to be useless as an ultrasonic vibrator. And as you can see up here on the right, talking about cyclical fatigue now, you have maximum applied stress versus number of cycles. This is found from a related study using PZT plates. And we used a linear regression model for a poled PZT plate and found 10 to the 30 cycles before failure at the maximum applied stress. And based on the frequency and operating time that we will be using, it comes out at about 10 to the 20 full operational cycles before failure. So it's safe to say that the design will not fail due to cyclical fatigue. And up here on the left, you have some important values that were found during the structural analysis. So we have the piezoelectric charge constant. This is going to relate to the piezoelectric effect, your degree of polarization versus stress. But for our case, we used, it's going to relate strain versus displacement of the plate. And we use that to calculate piezoelectric strain. And then using the Young's modulus of the PZT, we're able to calculate the stress. The coercive field strength is an important value for PZT plates in order to find where the actual dielectric strength of the material is, because you have to verify that experimentally based on the size of your plate and its thickness. So we could use that, multiply it by a factor of about 2 or 3 to estimate where your breakdown voltage is going to be. And this is going to be your dielectric strength. And doing that, we found the maximum applied voltage is going to be around 550 volts, which for an operating range for our design of between 100 and 200 volts is going to be a high factor of a safety of about 2.5. And again, here's just showing a quick overview of the equations used. So you have finding the strain using the piezoelectric constant. You have finding the stress using Young's modulus for a short circuit boundary condition. The linear regression models, finding the maximum stress. And then right here, you have breakdown voltage, which is relying on the breakdown strength and the thickness of the plate. which is relating to the coercive field. And for the thermal analysis, so PZT is actually pretty resistant to extreme temperatures, usually operating in a relative range of about between -40 and 150 degrees Celsius, which based on the landing times that are going to be done on the moon, which is going to be between about -7 and 20 degrees Celsius, shouldn't have an issue with that. And as long as your PZT doesn't exceed the Curie temperature, which is about 350 degrees Celsius, you won't undergo a failure of piezoelectric effects. And as well, humidity is going to be a major issue for PZT, which we really won't have to worry about because humidity on the lander is about 60%, which is below the max of 75%. And obviously outside the lander, it's a vacuum, so there's no humidity. And for the epoxy that we're going to be used to attach the PZT to our surface, we want to make sure you're using aerospace grade epoxy, which is low outgassing, which outgassing is basically a process by which an adhesive, when exposed to a vacuum or extreme temperatures, it's going to have a lot of air bubble formation inside of it, pretty much dissolve and liquefy all over your design, which we don't want, obviously. And the heat load for our design is going to be very minimal, about 6.82 BTU. And this is drawing approximately a watt from each PZT plate. So 4 watts total for 4 plates, operating at 30 minutes per cycle. Again, yeah, here's a quick overview of the thought process for the thermal analysis. So you have your total heat transfer rate is only 3.65 BTU per hour. And yeah, 6.82 per operation at 30 minutes. So this is going to be easily handled by the heat sink aboard the lander. So a thermal regulation system is not going to be necessary. Here you have your recommended range, the scheduled temperature during landing, and right there you have the temperature range for the aerospace grade epoxy, which is going to be more than enough to handle our design. For the power analysis, so we already said it's 4 watts for a 30-minute flight. And if this is going to be completely powered via solar panels, you're only going to need about 0.112 square meters of solar panel area, which is very minimal. It's going to be taking about 0.0033% of the power supply per single unit. So that's extremely negligible. And if multiple units are used, you're not going to impinge on the power supply of the lander at all. And yeah, so for our wave generator, we have an AC sinusoidal wave generator, excitation frequency of up to 100 kilohertz. So for our design, we found you want to have PZT plates between, as we said, about 25 to 80 kilohertz. This was one of the main limiters for our prototype, why we weren't able to use PZT plates. Basically, the thinner your plate is, you're going to need extremely high frequencies driving from your AC. So at a plate that we would have been able to acquire at that price range, we would have needed somewhere among basically 3,000 kilohertz around of range. And yeah, this is enough to handle the estimated voltage output of 100 volts for the amplifier. Yeah, and here's just showing the process for acquiring these values. We based our solar panel values off the ISS, which is producing 120 kilowatts per day, and it generates 35.7 per meter squared with the solar array. We have the area calculation right there, and again, we have each PZT plate is drawing 1 watt for 4 watts total, taking a very minimal amount of the power supply.
When it comes to the increased barrier of entry into the space exploration sphere, it is advantageous that a solution be low cost, which is why our solution, which equates to 9,000 USD per implementation, is a low cost solution for the Starship lander that, when compared to the $90 million total manufacturing cost of the Starship lander, equates to 0.01% of that total cost. When it comes to solutions, it is imperative that they be low weight, because any extra mass that you are adding to a spacecraft is taking away from the payload capacity. So our total weight for our solution is roughly 31 pounds per implementation, When you compare that to the Starship lander maximum payload capacity of 150 tons, that also equates to roughly 0.01% of that total payload capacity, leaving ample room for crew, cargo, and being minimally invasive to that total payload capacity. So when you are in space, there is a limited amount of resources. Therefore, it is crucial that a solution take as little of these resources as possible, which is why our implemented solution only deducts 4 watts over a 30-minute duration, leaving plenty of power supply for all the other systems on the Starship lander. This PZT solution has also been found in multiple scientific studies to be very effective, even more so than some of the current solutions on the market, such as EDS, ELDC, and Sparkle, and has also been found to be even more effective when combined with these current solutions, as working together, they can remove both ferrous and non-ferrous lunar regolith. A 2022 study produced by the Humanoid Research Center also concluded, in quote, that PZT is one of the most promising new technologies for removing dust from engines, cameras, windows, and landing systems. So since our solution is rather small and simple, we estimate about 1 year for development. After this developmental stage, we estimate about 6 months for testing and evaluation, just to make sure that it is properly scaled up to be effective on the windows and sensors on the Starship lander. And we think once these 2 steps are completed, we estimate that it will be able to be fully integrated into the Starship lander within a 3 to 5 year period, making it ready for their trip to the moon. Future applications. Not only can this solution be applied to cameras and sensors, but it can also be applied to any material really on the lander, whether that be the hull, the landing systems, you name it. One of our goals for this solution was to make it extremely versatile, minimally invasive, and being a solution that not only can tackle the issue of visibility impairment caused by lunar regolith, but can also be used in countless other areas in spacecraft and space exploration. So building upon that, this solution being, once again, both minimally invasive, small, not requiring much power output, and being very cost effective and low weight, can be applied to many mission critical systems off the lander as well as on the lander, such as rovers, landing pads, and spacesuits, making it an extremely versatile solution that, with continued proof of concept, can be scaled up and used on a multitude of areas within space exploration and bettering the future and making it easier for humans to make their way to the moon. Any questions?
Yeah, so I have this is Rick Miles from Northrop Grumman. So again, I'm not don't know a ton about piezoelectrics, but right with the lunar regolith, that it is very adhesive. So and it's based off the electrostatic forces, right? So what sort of testing would you plan on doing in order to be able to show that your piezoelectrics work with lunar regolith?
Well, to get a better test, we would have to do it in a vacuum. If you did it in a vacuum and you used the PZT and then you threw dust at the plate itself, it could show that it would be bouncing off of it, especially if you adjust the frequency of the electric field during that test so you can see what works the best. We, of course, couldn't get that exact and precise of a experiment, but I think what we did showed that it does work in theory. Did that answer your question?
So, and then I guess the other thing, right, is the smoothness of the surface is very key to how attractive the dust is as well. Anything about maybe just roughening up the surface so that it's not as attractive. I don't know. I mean,
Theoretically,
from a looking part of attractive, but just force is attractive, right?
right. I think even if it is smooth or rough, regardless, the vibration should be enough to bounce off any of the lunar regolith that attaches to it.
Okay. And then I'm a little bit of a English Nazi, so if you could go to slide 16. So dielectric instead of dialectic, right? So just always make sure you've gone through and looked through your slides to try and catch any of that stuff. Sometimes it's best to just have someone who's not familiar with the presentation look it over, because after a while you kind of start seeing things that aren't there. But you just don't want to show any errors in front of an audience, right? So
Absolutely. Thank you. Anything else?
Hey guys, as this is Tom Singer. I appreciate that you've put a lot of work in the last month. I think that shows in the improvements in the presentation that you made. I like seeing kind of the estimation of a Windows natural frequency. I think that was important to the presentation. I like that you put together a proof of concept. I think it certainly is not a definitive test, but it's something. I can certainly appreciate that it's difficult to put together a test that would really be representative of the electrostatic properties of regolith in vacuum and a low G environment. But I appreciate you putting something together for that. So you're envisioning having 4 of these like at the corners of each window?
Yeah, that's the current plan. That way, if one is exposed to failure, there are 3 that can still be effective.
Okay, so
Oh,
how,
four plates. Specify 4 plates with 1 component box.
wait ahead. Okay, so four plates, 1 at each corner of a rectangular window?
Yeah.
Or 4 plates at each of 4 corners?
Yeah, 1 at each corner, yeah.
Okay. So how are you sizing these, right? So do you have an estimation of how much you need to actually, beyond the frequency, like the amplitude that you need to vibrate a window at in order to successfully remove dust?
So for the study that we based our experiment on, they use PZT plates, which are about to get in you want to be in like that frequency range to where you can handle it with an AC amplifier. So and you also like the thicker the plate, the more like vibration you're gonna have to overcome those adhesion forces. So if we were to make an actual prototype, it's gonna have to be between about like a 1/4 inch to 1/2 inch thick. And this is based off there's actually another constant which I didn't include in the structural analysis. It's called like piezoelectric frequency constant. Basically, it relates the thickness of your plate to the natural frequency of the PZT. And based off of a 1/4 inch, that's going to sit between our 30 to 80 kilohertz range that we said earlier.
Okay, well, I'm thinking more from the perspective of the window, right? I mean, I could put in 30 kilohertz at next to no amplitude, and it's not going to do anything, right? And I put in 30 kilohertz at some huge amount of amplitude, and it just like breaks the window, right?
Yeah.
There's going to be some amplitude that is going to be optimal for removing dust, some amplitude and frequency that's going to be optimal for removing dust. So are you doing anything to size that, or are you just saying, well, we've got 4 corners, so we're going to put, 4 pads of material there, and we get what we get?
So for the idea with the 4 plates at the corner is you're having them all oscillate and it creates like a standing wave across the entire surface. So that's definitely going to be based on, I feel like for each individual case, it's going to be based on like the total size of the window or whatever surface you're operating on. And it's probably going to be a different frequency and amplitude for each. I feel like that would have to be mainly found through experimental testing.
Okay.
I don't think we had like the resources to fully find out what those values would be.
Yeah. So the thing about standing waves, and I'm glad you kind of brought that up, right? The thing about standing waves is you're going to have nodes in the window that aren't moving at all, right? I mean, that's the idea behind the standing wave is that you get a wave that would normally be traveling, but because of the interference effects, it just doesn't go anywhere. So you're going to have nodes or geometric patterns on your window that aren't vibrating, where you're not actually clearing dust. So I wondered, would your system have some ability to tune the frequency or tune the phase of the individual oscillators in order to kind of sweep that wave across the window?
So in the study that we based our design off of, so they did 2 tests for it. They did a standing wave, like you said, which would have nodes in it, and they also did a traveling wave at the same time. So they did for those 2 cases, and they found that it was actually, at least in their case, it was negligible doing the standing versus the traveling wave. But you can actually you can set it up with all the right to where it would be, you'd kind of have, I think they did the top and bottoms out of phase, or the left and right, and it would create one traveling across. And I think that would kind of get rid of the node anti-node issue right there.
One little note, they did also find that it was very effective to use both traveling and standing waves.
Yeah.
Okay.
Negligible difference between them for that specific experiment.
Okay. And then you had a weight of 31 pounds, and I guess that's per set of 4 of these. And I think we talked a month ago, and you said that was just a very conservative estimate of weight. Do you have anything more refined than that, or are we really thinking that this is going to hit 31 pounds of material that you're adding to the spacecraft?
Yes. So in our previous report, we estimated it would be roughly 52 pounds. But then for one of our weekly reports, we were going in and finding the specific components online and where you could purchase them. That's where we got the new cost and the new weight estimate. So it actually is most likely going to be less than that 31 pounds because everything in the component box comes to 30 or to 26 pounds. And then we estimated an extra 5 pounds for the wires and the PZT plates, which are most likely lighter than that.
Okay, so the component box is the majority of the weight, and that's basically the electronics that are controlling the piezoelectric system.
Yes, sir. Also, as a small note to that, as if it were to be adopted by SpaceX or Blue Origin, they could further refine those electronics. We tried to use standardized parts because we didn't possess the electrical knowledge to really go after how to design the circuits to be hyper optimized to do what we needed to do. So we ran into the restriction of standard parts not being the most accurate for what we needed. That's why we made it as conservative as possible.
Okay, so then the next question becomes: a spacecraft is going to have more than one surface that it wants to clear dust from, correct?
Yes, sir.
So are your electronics, or do you need a separate 30-pound box of electronics per window, or is that something that could control multiple systems either simultaneously or sequentially if you didn't need a real-time clearing?
Right, so with the system that we have created, you would need a separate implementation because it is a separate thing. It would be using different voltage regulator, different signal generator. It would be outputting a different frequency for a different material. So in our case, yes, I imagine if it was actually adopted, they would find a more efficient way to use just one component box, which has its own parts, and then connect it to both. But for our purposes, it would have to be separate for each implementation.
Okay. Okay, because when you're quoting 30 pounds, right, I think it's calling that 30 pounds is only a small percentage of your payload mass, which good job on that this time, guys. The system that gets adopted is going to need to be effective for more than one place. So I think it's important to highlight, what a typical lander might have. I don't know if you have any information about how many windows or whatever other panels you might need to clear, but I think it's important to kind of characterize it in those terms.
On the SpaceX one, a lot of the information was proprietary, so it's hard to find.
Yeah.
Yeah, so we kind of based a lot of our stuff on like the early Apollo missions. And the main surface that we were targeting early on, it's called like the lunar something like view area. It's basically where they have the camera down that's doing your visibility. That's the main surface we were focusing on initially. We weren't able to find anything based on other surfaces for the SpaceX lander. But yeah, that one visibility surface is what we were mainly focusing on for this design.
Okay.
But since you weren't able to find that specific information, we kind of just generalized it by saying, that was the price per implementation, or, the weight per implementation. So it's kind of like, the price and weight per surface that it'll be implemented on.
Okay, that's all I've got.
Thank you.
Thank you.
Thank you.
Thank you so much.
This something first really complex, which I think it's much better than last time. It's just like here it's 25 minutes, and also like I feel the introduction part is too long because I want to introduction is good because you get people familiar with whatever in here, but I checked, it's like the first 8 pages is the introduction, and it's like 7 minutes into presentation, you're not talking about your own design yet. And it's like 7 minutes out of 25 minutes is something like bedrock introduction. And also this kind of information also repeated at very end, it's like low cost, low weight, low power. So I would consider like if you only have like 25 minutes presentation, I would more focus on design. Yeah, I would say introduction like background, different technology, what damage of the last everything within 2 minutes. And more focus on design because those kind of information should not take like information. And for the details, can go to the page together. Yeah, it's good that it could exactly this here. I really like just want to see some information, but I'm just curious, what is 90%?
90% was our goal. Oh, yes, 90% was the, I'm sorry, I should have specified. 90% was the goal going into it of dust removal that we're looking for. And then based on experiments and other research, we discovered it would be higher in the 95 to 99% range. Yes. Yeah. Yeah. So 90% was the goal. What we actually achieved was 95 to 99.
Page 16. I'm really happy to see here some analysis and criteria and everything because these I think is very important for your division. The thing is that you have massive SN equal to a and to part B, and you calculate you have 10 to 30 cycles. I don't think you can really. I think the calculation itself is like it's not correct because the equation itself is only for the range of high sensitivity. What range of high sensitivity is 1,000 to 10⁶. And any calculation beyond that range cannot use this equation. 10 to 30 is not really in the range that we can use this equation. You know what I mean?
Oh, yeah. So for that, this was like really the only SN chart I could find for PZT.
Yes. For most material in general, low cycle fatigue is lower than 1,000 cycles. High cycle fatigue is 1,026. And
So
most material after 26 is injurious limit. So everything that older than that, I would say that is around forever.
well, yeah, PZT, that probably is a little on the high end, but we really wanted to get an SN chart to show like some actual like physical calculation for it. But all the research that when I've looked up for PZT actuators, which is pretty much thing in your toothbrush that oscillates, and for oscillating like PZT material, it's usually on like the order of billions of cycles. So these things pretty much never fail from my research, never fail due to cyclical fatigue. But yeah, I mean,
Equation itself has cycle fatigue. The R is 26. Higher than 26, you cannot use equation.
oh yeah, it was just, we took like that pulled line and pretty much did a linear model because all these applied stresses you have, right? Yeah.
It would not be like for whole.
Yeah.
No, it would not. For research on that, I don't think it's like it's for whole range. No.
Oh no, I agree. It was really hard to find like a lot of data for this.
Yeah.
So this is what, yeah.
They just say it would run there. Or
Yeah.
you just say,
Well,
okay, my stress level is all the induced limit.
Yeah.
Then you're done. And
Yeah.
also one thing I'm a little confused about here is that places we have the stress, is that stress that actually calculated by the voltage? Or and the stress
This is the piezoelectric stress. This is the stress caused purely by the oscillations of the inverse piezoelectric effect.
actually, that is the actual stress in your stress.
Yeah.
So you use that stress level to calculate the
Oh, yeah.
That's detect and
Oh wait, no. So I took, you see, yeah, so 18. So this one only goes, it's obviously really high level. So I did base it off that 18.92.
yeah. So the question there is massive sub A times N power. So basically you have the COX and you use the equation to calculate it.
Yeah.
Then go to page 17. Because I remember when you talk about who present this slide, when you guys talk about these slides, you said you use this equation to calculate stress. I mean, why is stress calculate number cycle? Now you use number cycle to calculate stress. I don't know what you are doing either.
Oh, for what? Oh.
You use calculate number cycle. Now you use this equation again to calculate stress. I don't understand.
Oh, it should be NF and then sigma max right there. Pretty sure. I think that's a mistake actually.
No, then the equation.
But
The equation should be go back to the page.
But-
That equation is correct. Actually it's the formula correct. I don't know the exact correction, but it's Sn equal to A times NF to the power B. And go to the next page. Something wrong here. I don't know.
yeah.
Something wrong.
Yeah, man. I don't know. Because it's a logarithmic chart, so it did linear regression model accounting for that. And then I think the stress should be inside that log right there, I'm pretty sure. But yeah, I don't know what went wrong there.
Do you use stress calculate number cycles? So do you use number cycles? You have 20 number cycles to calculate stress.
No, we use stress to calculate numbers. Yeah. Yeah, that must be an error right there. But basically, like the moral of the story with this one is like it's not going to fail due to cyclical fatigue. It's going to be like, yeah. Yeah, sorry about that.
And page 18. So the third one analysis, you show the third one is minimal at. Why do you want some minimal heat loads when you do some preparation. Would that
Oh.
actually use maximum?
Oh, no, I'm saying that it's a very minimal heat, like it's not gonna be outputting a lot of heat, so the heat sinks aboard the lander are gonna be, you're not gonna need like a separate thermal regulation system. Yeah,
That.
yeah,
is-
that's worded badly. my
That
bad.
is actually much higher than what the max is. We use a 30-minute max operating time. Based on my research, 10 minutes for the whole entire journey would be more likely, but if there was some problem and they had to make landing longer, 30 minutes would be the max. So we use that, but it would in practice be.
Yeah, because when I see that one, I think this is like minimal. I mean,
Right.
when you do some thermal analysis and then you want to generate this much of heat loads, and you want to say, okay, what's maximum and what's the measurability, what's that? And I generate maximum of this is not minimum. That's my. basic
Yeah.
logic.
Yeah.
The max.
Yeah, I meant to put like, it's a very minimal heat load, it's not gonna, yeah. My bad.
And page 20. So for the power analysis, you calculate 0.2112 minutes for solar panel. I mean, if it's this kind, do you really need a separate solar panel to support your design, or you just use power system?
No, you would be using, you just, this was just to show exactly how much of the present solar panel would be diverted to just use this, yes. No, that you wouldn't be adding that to it, no.
Into what is already there.
Okay.
That was the whole point of us talking about how minimally invasive it is,
Okay.
so it's to show that it can integrate easier into those systems.
And
Probably I was concerned about it is why I thought, hey, I think solar panel delivery is so.
Well, I think on the next slide.
Yeah.
Yeah.
And that's where that point.
the SpaceX one should actually be more efficient.
Again, just to like hammer home how like minimal power requirement it is.
Yeah, even if with the old ISS technology, it would still be minimal. So with the new technology, it can only be better.
That's all the question I have. I think it will be a great job. I really glad that you have the added all of stuff like equations and technical stuff here. It's so much better than last time. And actually, mom,
Oh, your mom was.
That's what they haven't responded to me. I told them they could ask questions.
They have no question.
Any last minute questions, audience? No, okay.
There is one thing I did forget to mention. The component box will be protected by multi-layer insulation to
And the
protect it
liquid
from
cooling.
radiation. I forgot to mention that in my